It has long been recognized that certain glyphs in the text of the Voynich Manuscript have uneven positional distributions within lines and paragraphs. Well-known examples include the tendency of paragraphs to begin with a gallows glyph, most often P, the preference of P and F for the first lines of paragraphs, the preference of M and G for the ends of lines, and differences between the relative frequencies of glyphs found respectively at the beginnings of line initial words and of midline words. Note that I'll be referring here to glyphs using the names of letters in the widely used extensible Voynich alphabet, or EVA. For convenience, I'll also refer here to patterns of uneven positional distribution within lines and paragraphs, simply as distribution patterns. At first, the identification of distribution patterns was restricted to distinctive behaviors at the extremities of the text. The first and last glyphs of the line, the first word in the line, or the first line of the paragraph. This limitation left open the possibility that the patterns might represent narrowly isolatable contextual modifications made to the edges of text that is otherwise uniform in character. During the past decade, however, distribution patterns have begun to be detected deeper inside lines as well. Elmar Vogt reports that the second words of lines tend to be shorter than average. Emma May Smith and Marco Ponzi find that the second words of lines in Quire 20 begin disproportionately with SH and CH, and J.K. Peterson observes that AN, AIN, and AIIN tend to appear later in lines than ON, OIN, and OIIN. Occasional findings such as these have hinted that distribution patterns might be more pervasive than formerly suspected, implicating much or even all of the text, and that they are accordingly all the more deserving of methodical study. In this presentation, I'd like to discuss some recent efforts I've made to systematize the search for distribution patterns among words and glyphs. My approach centers on the use of two convenient quantitative metrics, rightwardness and downwardness, which can be reported as numerical scores or plotted on graphs of various kinds. I'll start with rightwardness. What I mean by this is how far towards the right end of a line a word or glyph appears. In the past, this parameter has typically been discussed in terms of absolute positions, such as the second word in a line or the second to last word in a line. Absolute positions might well be significant, but they're cumbersome to analyze. Any word could be associated with either of two numbers, depending on whether positions are counted from the left or the right, and lines containing different numbers of words can be difficult to compare with each other in these terms. Thus, I've chosen instead to analyze relative rightwardness, or how far towards the right a token appears proportionally within a line, a metric that permits easier comparison across disparate contexts. Relative rightwardness can be calculated by dividing a token's ordinal position within its line, counted from left to right starting at 0, by the line's total token count minus 1. If we assume for purposes of argument that Voynichese text runs from left to right, a token at the beginning of a line will always score 0, a token at the end of a line will always score 1, and a token in the exact middle of a line will always score 0.5. To demonstrate the process of calculation more concretely, let's turn to folio 103 verso, line 2 as an example. There are two tokens here of SHEY, the second and seventh out of 11 words, so their individual relative rightwardness scores are 1/10 and 6/10, and the mean of these two scores is 7/20, or 0.35. One object I found it especially productive to study in terms of relative rightwardness is the graphemic minimal word pair. By this I mean a pair of words that are formally identical except for a single grapheme, such as CHOL versus CHAL, much as a minimal pair in phonology refers to two words that differ only by a single phoneme or other phonological element. For convenience, I'll refer to graphemic minimal word pairs here simply as word pairs, and to words belonging to such pairs as homologous to each other. And I'll further define a word pair set as consisting of all attested word pairs that differ in the same way, such as by beginning alternately with SH and CH. If we compare mean rightwardness scores, either for individual word pairs or for whole sets of them, we find that words that contrast in the same way sometimes display consistent positional deviations relative to one another, with one type routinely scoring rightward of the other. The deviations themselves might be very slight, perhaps corresponding to an average difference in position of only 1/20th of a line. What's remarkable is not their magnitude, but their consistency. Rather than spending the time available to me here today trying to identify and list as many distribution patterns as possible, I'd like to focus on establishing the existence of 3 presumptively representative ones as persuasively as I can. The statistics that follow were obtained by applying custom Python scripts to the Zandbergen-Landini transcription of the Voynich Manuscript, version 1.7, omitting commas that represent uncertain spaces, and limiting analysis to text in paragraphs, as opposed to circles, labels, radii, and so forth. First, words beginning with ch routinely score rightward of homologous words beginning with sh. If we calculate mean relative rightwardness for both of the pertinent word pair sets, the sh set scores 0.434 with 2,456 tokens, while the ch set scores 0.514 with 4,050 tokens, showing a difference of about 0.08. These figures include the first and last words of lines, and since words in those two positions have long been recognized as displaying anomalous behavior, it might be tempting to assume that the difference in score results from them alone. However, if we exclude all scores of 0 and 1, limiting our analysis to what I will call midline words, the sh set scores 0.433 with 2,167 tokens, while the ch set scores 0.481 with 3,600 tokens, which still shows a difference of about 0.05. If we compare specific word pairs, we find that the pairs with the highest total token counts conform individually to the same pattern. There are 21 word pairs that alternate between initial sh and ch, with 60 or more total tokens, and in every one of these cases the ch word scores rightward on average from the sh word. If we limit our analysis to midline words, 19 of these word pairs, roughly 90%, still conform to the same pattern. Second, words beginning with o routinely score rightward of homologous words beginning with qo. If we calculate mean relative rightwardness for both of the pertinent word pair sets, the QO set scores 0.468, while the O set scores 0.534, showing a difference of about 0.07. If we limit our analysis to midline words, the QO set scores 0.487, while the O set scores 0.517, which still shows a difference of about 0.03. If we compare specific word pairs, we again find that the pairs with the highest total token counts conform individually to the same pattern. There are 23 word pairs that alternate between initial QO and O with 100 or more total tokens, and in every one of these cases, the O word scores rightward on average from the QO word. If we limit our analysis to midline words, 19 of these word pairs, roughly 83%, still conform to the same pattern. Third, words containing t routinely score rightward of homologous words containing k. If we calculate mean relative rightwardness for both of the pertinent word pair sets, the k set scores 0.488, while the t set scores 0.523, showing a difference of about 0.035. If we limit our analysis to midline words, the k set scores 0.490, while the t set scores 0.541. which shows a difference of about 0.05. In this case, then, the difference in mean scores actually increases when we consider only midline tokens. If we compare specific word pairs, we find that the pairs with the highest total token counts follow this same pattern. There are 22 word pairs that alternate between k and t with 100 or more total tokens. Overall, the T word scores rightward on average from the K word in just 16 of these cases, about 73%. But that figure increases to 20 cases, about 91%, if we limit our analysis to midline tokens. It's worth emphasizing that a single word can contain more than one of the elements associated with the 3 patterns I've just outlined. For example, it might begin with ch and also contain k. When this happens, the word's distribution will necessarily conform to both patterns simultaneously, unless it's anomalous with respect to one or the other of them. Particularly when we bear this situation in mind, it appears that positional constraints must be operating independently on component parts of words, rather than on words as unitary wholes, implying that the affected words are behaving to a surprising degree as nothing more than the sums of their parts. The scoring method on which I focused here so far can be used to detect differences in the average positions of words, glyphs, and other textual units, but it tells us frustratingly little about those differences. In particular, it reveals nothing about the specific patterns of distribution within the line that must be responsible for the discrepancies we've observed between whole line and midline scores. If we want to draw out such additional details for study, one option we have is to create a graph in which the x-axis represents relative rightwardness quantized into some number of bins, and the y-axis represents the ratio of pertinent tokens to total tokens within each bin. Each point on the graph can then show the proportion of tokens in some particular part of the line that satisfy a given criterion on a scale ranging from 0, none of them, to 1, all of them. If we organize and display our data in this way, we find that distribution patterns can, in fact, have distinct shapes. For the examples of this type I'll be presenting here, I've assigned a rightwardness score of 0 to the first bin, a rightwardness score of 1 to the last bin, and 8 equal divisions of the intervening range of scores to 8 bins in the middle. Thus, bins 1 and 10 represent the two extremities, while bins 2 through 9 represent the midline. In every case, the sharpest jumps all occur between the extremities and the nearest parts of the midline, which reinforces the perception that behavior at the extremities is especially anomalous, and I believe justifies the decision to separate out those positions analytically. However, distinct patterns can be seen in the midline as well, and those are the ones in which I want to focus here. From this first graph, we learn that the proportions of homologous words beginning with sh and ch both peak at the far left of the midline, and then decrease progressively towards the right. The lower mean relative rightwardness score of the sh set turns out to be due to its proportion decreasing more steeply from left to right than that of the ch set. The next graph reveals that, among homologous words that alternate between k and t, the k set peaks just to the left of center, whereas the t set increases gradually in proportion from the left to right of the midline by a factor of about 1.5. This final graph shows that, among homologous words that begin alternately with qo and o, the o set peaks at the left and right of the midline with a dip in the middle, whereas the qo set shows the opposite trajectory, peaking in the middle with dips at the left and the right. These patterns aren't quite symmetrical, however, and the o set rises above the qo set for longer on the right than it does on the left, which I assume is the source of its higher mean relative rightwardness score. If the patterns had been more symmetrical, their left and right halves might instead have cancelled each other out in scoring. Graphs such as these can provide more nuanced information about the distribution patterns detected by our earlier scoring method, and they also have the potential to reveal further distribution patterns to which our earlier scoring method wouldn't be sensitive, such as horizontally symmetrical ones. The graphs we've been looking at still have a serious limitation. Some of the best-known distribution patterns, such as the preference of P and F for the first lines of paragraphs, are tied not to rightwardness, but to a second dimension perpendicular to it, which we can call downwardness. Relative downwardness complements, and is analogous to, relative rightwardness. It measures how far proportionally towards the bottom a token appears within a paragraph, and it can be calculated by dividing the number of the line in which a token occurs, counted from top to bottom starting at 0, by the total quantity of lines in its paragraph minus 1. Any token in the top line will score 0, any token in the bottom line will score 1, and any token in a line at the exact center of the paragraph will score 0.5. The approach I've settled on for simultaneously visualizing rightwardness and downwardness entails, first, generating a row of pixels for each line of text, with a bright pixel representing each token of the target element, and a dark pixel representing anything else. Second, stretching the row horizontally to the width of a square. Third, stacking the rows representing each paragraph and stretching the stack vertically to the height of a square. And then, fourth, overlaying and averaging the stretched images for all paragraphs. The result is a square grayscale image in which brighter or darker areas correspond to relative positions rightward and downward, where the target element is more or less prevalent. One reason for mapping quantity to brightness rather than darkness is that we can then assign the results for multiple target elements to different color channels in a single image, so that contrasts of color will correspond vividly to mutual differences in distribution, making these easier to discern. I also find that it can once again be advantageous to separate out the extremities, which in this case means assigning them to their own rows and columns, and treating only mid-line tokens and mid-paragraph lines relatively. The visualizations you see here each present two sets of results using the red and blue channels of a standard RGB image. They cover the same three contrastive word categories as before, although this time I've included all words that fit the criteria in question, such as beginning with CH or containing K, rather than limiting the scope of analysis to homologous word pairs as before. These visualizations reinforce some of our earlier observations about distribution patterns, but they also enable us to make some new ones. Words beginning with SH turn out to be distinctly more prevalent in the first lines of paragraphs than words beginning with CH, even though they're consistently less prevalent in lower lines. And the average positions of words containing K and T also contrast more conspicuously there than elsewhere. Words beginning with QO appear noticeably more often as the first words of lines towards the center of paragraphs than they do further upward or downward. Finally, in all three cases, the proportion of the words being studied doesn't decrease sharply at the last position in the last line of the paragraph, as it does at the last positions in all other lines, and sometimes it even increases there. It's commonly recognized that the sequence of glyphs within a Voynichese word is constrained by rather rigid morphological rules. From the foregoing evidence, however, it seems that the presence of specific glyphs within words is simultaneously constrained by additional forces operating throughout the text at the line and paragraph levels. Numerous glyph types can be shown to appear preferentially in certain parts of lines and paragraphs as opposed to others, perhaps causing words containing them to show similar distributions as a secondary effect. When it comes to explaining distribution patterns, there are various possibilities we might entertain. One is that each line of text corresponds to some unit of meaningfully patterned content, such as a grammatical sentence, a line of poetry, or an entry in a list. Exploratory studies of a few well-known works of poetry show that similar patterns can be detected in them, presumably due to a complex interplay of grammatical, metrical, and stylistic factors. In Virgil's Aeneid, for example, if we compare homologous word pair sets ending ES and IBUS, the ES set has a midline average rightwardness score of 0.399 with 343 tokens, while the IBUS set scores 0.708 with 390 tokens, a difference as stark as any we've considered in connection with the Voynich manuscript. Alternatively, we might hypothesize that distribution patterns arose as a byproduct of some method of encoding meaningful content, rather than from the content itself. Here I'll cite just one representative scenario. 15th century ciphers often sought to increase security by providing multiple options for encoding each plaintext character, and for this ploy to work as intended, a writer needed to alternate repeatedly among those options. One strategy for ensuring that happened would have been to favor different options in different areas of the page. Thus, there's more than one angle from which we could try to explain distribution patterns, but the methods I've outlined here for identifying such patterns should, I hope, be equally applicable to any and all prospective interpretations of them.